In question 5, we're given this diagram here of a piece of cardboard, and in the big block of text at the beginning, we're given the dimensions of that piece of cardboard, 31 centimeters by 22 centimeters. We're told the box is to have a capacity of 500 centimeters cubed, but that doesn't come in until a little bit later. The shaded areas are flaps of width 1 centimeters, so that's that little width there. The height of the box is h centimeters, that's that and that, the same for each of the sides. And we're asked to write the dimensions of the box in centimeters in terms of h. Well, we're given a freebie right at the beginning. We're told that the height is h centimeters. And now what I'm going to do is consider the width to be in this direction and the length to be in this direction. So one of the first things I can write then is that 31 is equal to, first of all we have the little 1 centimeter bit. Then I'm going to say that this dimension here is w, the width. Then we have this here is h, and another width, w, and one more h. So then we can do a bit of rearranging and say that w is equal to 15 minus h. Now we can also figure out the length in terms of h. We can start with the 22, and we know that first of all there's a little 1 there, and then there's a h. I'm going to consider this to be the length L. Then we have a h, and lastly another 1. And again we can do a little bit of rearranging here, and we just end up with L is equal to 20 minus 2h. Now we have to write an expression for the capacity of the box in cubic centimeters in terms of h. Another word for capacity is volume, and we know the volume of a box is given by the product of the three dimensions, so V is equal to h times L times W. We know h is just h, L is 20 minus 2h, and w is 15 minus h. And I'm just going to leave it like that for the moment. There's no need to start multiplying all this stuff out quite yet. Now we're asked to show the value of h that gives a box with a square bottom will give the correct capacity. First of all, recall that the correct capacity is 500 centimeters cubed, and a square bottom means that the length and the width are the same. So first of all we can say that L is equal to W. That means that 20 minus 2h is equal to 15 minus h. And now we can solve for h. We get 5 centimeters. That's just a little bit of rearranging. Using that bit of information then we can work out that the volume is h first of all, which is 5. That's multiplied by 20 minus 2 times 5, and that's multiplied by 15 minus 5. I'm just getting that formula from part B. So we get 5, and that's multiplied by 20 minus 10, which is just 10, and that's multiplied by 15 minus 5, which is also 10. So we get 500 centimeters cubed, which is exactly what we were asked to find. Now we're asked to find, correct to one decimal place, the other value of h that gives a box of the correct capacity. Well, now I'm going to do that multiplication. I'm going to start with V is equal to h times 20 minus 2h times 15 minus h. Multiply that h in first, so I get 20h minus 2h squared. That's a square. And that's times 15 minus h. And that gets me 300h minus 20h squared minus 30h squared plus 2h cubed. And we know that that's equal to 500 because that's the correct capacity that we were told at the beginning. So I can do a little bit of rearranging there and do a little bit of division as well while I'm at it, and I get that h cubed minus 25h squared plus 150h minus 250 is equal to 0. Now I know that h is equal to 5 is a valid solution here, so I can do some algebraic long division here. So there's h minus 5. Remember, this is the factor form of the root h equals 5. I'm dividing that into all of this, the h cubed minus 25h squared plus 150h minus 250. So first of all, h into h cubed goes h squared times. H squared times h is h cubed. H squared times minus 5 is minus 5h squared. Now I change those signs and draw the line that tells me that I need to add them. So those two are going to cancel. And now I have minus 25h squared plus 5h squared. So I get minus 20h squared. And I can bring this down, so I have plus 150h. Now h into minus 20h squared naturally goes minus 20h times. So minus 20h times h gets me minus 20h squared. The minus 20h times minus 5 gets me plus 100h. Now I can change those signs and draw the line. So minus 20h squared plus 20h squared is going to cancel. And now I have plus 150h minus 100h, so that gets me 50h. And I can bring this down, so I get minus 250. Now h into 50h goes plus 50 times. And 50 times h is 50h. 50 times minus 5 is minus 250. And just as a last checking measure, I change the signs and draw the line. So they cancel and they cancel. And so I have a remainder of 0 at the end, which means that this divides evenly. Now with this information, now I have a quadratic expression that you can test it, but it's not factorizable, so I'm going to have to use the quadratic formula to figure out what values of h are going to satisfy this expression. So I can say that h is equal to 20 plus or minus the square root of minus 20 squared minus 4 times 1 times 50. That's all divided by 2. So that gets me 10 plus or minus 5 root 2. So that gets me two different answers. There's 17.1 or 3.0. Now, if you'll remember, at the beginning of the question we were told to find the other value of h that gives a box of the correct capacity. So there's only one value of h that's valid here. So we're going to have to eliminate one of these two. Now remember, we figured out a while ago that w was equal to 15 minus h. So if h is 17.1, that means that w is minus 2.1. But lengths can't be negative, so that means that 17.1 is not a valid answer, and h is equal to 3 is the only other valid answer. Now in part E, we're told the company wants to make a box that's 10% larger in terms of its volume, but it wants to use exactly the same piece of cardboard, has the same dimensions, 31 by 22 centimeters. This graph here shows the capacity as a function of h, and we have to use the graph to explain why it's not possible to make the larger box from a piece of cardboard. Well, first of all, the new capacity is 500 plus 10%, which is 550. Now, notice here is about 550. If you bring that across here, you notice it only crosses this graph at one point. And that's where the issue lies. There's only one possible value of h that will give this capacity of 550, and that's 17 point something. But remember, we ruled out any values of h that were greater than 15 or so, because that's going to make our width negative. And in fact, we can rule out any values that are greater than 10, because that's when our length is going to be negative. So only values of h between 0 and 10 could possibly be valid solutions. And notice that no value of h is actually going to reach this blue bar here at 550. So you can say something like the local maximum value of h gives a volume of lower than 550, so no value of h below 15 centimeters can be used to make this box. A value of 17 centimeters or so would be sufficient to make the box, but it's not possible because that would require negative widths. Or you could reference any value greater than 10 because that will get you negative length.